Hi everyone, my name is Elizabeth Amona. Um, I'm a PhD student at Virginia Commonwealth University, USA. I'll be speaking on the title Incorporating Interventions to an Extended Shared Model with Vaccination. So this work is I'll be applying it to COVID-19 dataset in the state of Qatar. Here is the outline of my presentation. I will start with a very brief introduction, then I would move in this order until I get to the discussion, and I will conclude from there. I know that we are all familiar with COVID, we know a lot about it, so I wouldn't want to bore you with too much information, but I would like to mention that COVID-19 is a severe pandemic that actually affected the whole world and is still affecting the whole world, at large. And as a result, taking precaution is inevitable. Despite that, the government of Qatar and even all other countries, intervene in one way or the other. But I'm focusing on Qatar, so I'll be focusing more on Qatar intervention in this talk. Despite that, the government, intervene in so many ways by closing down universities, recreational centers, travel bans, and all other interventions. We still realize that a lot of people um, are getting infected. That is, the number of infected cases keeps increasing. And this leads to the question that were there any intervention measures that were really helpful in reducing this transmission rate, or were there intervention measures that were not necessary at all? So this is one thing we want to understand in this work, and one way to do is into incorporate intervention into the model for us to be able to make inference and to be able to determine the interventions that were helpful in reducing the transmission rate and the ones that didn't do anything or probably increased it a little bit. And that is the main focus of this study. In order to do this, I'll first mention the um, assumptions of the model, which is important before we set up the mathematical model. There are lots of assumptions here. I would like to mention a few of these assumptions because of the time. First, I would want to mention that the immigration and the birth rate is excluded in this model because of the time frame that we considered. So we didn't consider the immigration and the birth rate. And also, looking at the last assumption, once someone is vaccinated, the individual remain insusceptible to the disease during the study time. So this is another assumption that we have actually relaxed in the ongoing work. So most of these assumptions have been relaxed in the ongoing work, and we allow for more mixing and interaction between the states. All right, and here is the definition of the states that I'll be considering in this model. And the first one is S, which we all know is the susceptible. The exposed is the E. The infected is the I. Then RE is these are those who recovered after they got exposed, and after they got infected, those who recovered, they are the RI, and those who died as a result of the pandemic, they are the D, and vaccination, those who got the vaccine. So that is the V. Here is the systems of equation. I know that most people might not be familiar with this, or it might not be easy to understand the system of equation. So I have a schematic diagram that would help us to understand this better. Um, we assume that everyone is susceptible, right? And everyone can get vaccinated. That is, all those who are susceptible can get vaccinated at the rate of rho. When someone is exposed, the person moves from the susceptible compartment to the exposed compartment at the rate of alpha. And those who are exposed could get vaccinated. Um, those who are exposed are the asymptomatic. They do not, they are not sick, so they don't know if they are infected or not. But once they become symptomatic, they move to the infected compartment at the rate of beta. These ones could recover at the rate of gamma or die at the age of zeta. I forgot to mention that those who got exposed could also recover at the rate of gamma. And this is the movement from one compartment or the other. Right, a little bit about the data set. We got this data set from the Johns Hopkins University GitHub site. And one thing I would like to mention here is that for us to get the actively infected individual, we have to subtract the cumulative infected from the recovered and death. With this, we can get the actively infected individual. Otherwise, the analysis might be incorrect if we do not take the step. Right. Here's just the diagram of the data set that we got from the JSU website. If you look at the infected individual, you would see an interesting behavior. There's a huge spike at some point, huge jump, and there's a plateau until after day 300 where there's another increase. This tells us that something is actually happening. Maybe there were intervention measures taken by the government that helped to reduce this transmission rate, or maybe that was something that happened that caused the huge increase. These are the interesting things that we want our model to explain to us. And going forward, we'll be talking more on the model. And in the right hand side, we have the recovered. Here we have the dead and the vaccinated. Like I said, the main focus of this work is intervention. The intervention measure placed by the government and the ones that probably, if the government has placed, maybe this would have helped to reduce the transmission rate. There are several ways to introduce intervention to mathematical model, but one way that we want to introduce ours is the use of indicator functions. That is equation 3. One important thing on this slide is the transmission rate. I would like to mention that the transmission rate, which is the alpha, this is the parameter that the government can actually influence. By the time they place interventions, by the time they come up with policies, their policy can affect this transmission rate. And that is why we'll be focusing on this transmission rate in order for us to understand the impact of the policies made by the government on the transmission. And going forward, our focus will be more on the alphas. When you say the alpha naught, it means that what is the transmission rate before any intervention measure was deployed? And alpha 1 means after the first intervention measure, what is the transmission rate? This tells us that the transmission rate is going to change as different intervention measure is being deployed by the government. All right, and this goes on and on until we get to alpha k. Another thing to mention about this transmission rate is that they are independent of each other, and this is just the mathematical representation of the transmission rate. The method that will be used for the analysis of this work will be the Bayesian analysis framework. We'll be using this due to the complexity of the model. And if we are familiar with Bayesian analysis, we know that the formula is the posterior distribution is approximately the product of the likelihood and the prior. All right, so that is the formula for the Bayesian analysis framework. And talking about the likelihood is always with respect to the state that you are interested in. And in our case, the state is the infected, the recovered, the deaf, and the vaccinated. Notice that we do not have the exposed and the susceptible here. And the reason is because we do not have this information in the data set. So these two states are latent in this analysis. And for the prior, we have the parameters, which are the alphas, the betas, the gammas, and the rho and the zeta. Since the posterior distribution do not lend to any analytical solution, we'll be using the MCMC technique in order to sample from the posterior distribution. Particularly, we'll be using the Metropolis H2 sampler in order for us to sample from the posterior distribution. There's so many things we need to understand about this method, but because of the time, I wouldn't want to say a lot on this slide. But one thing I would like to mention is that this method is computationally kind of intensive because it takes longer time. But the good thing is that the result is always, I mean, not always, but reasonably good. It fits quite well. And we'll see this in the results section. This is the first result. We got a pseudo R square of 0.999, which means that the model that we got fits the data quite well, which is impressive. And looking at this result, you would hardly tell if there's any difference between the fitted and the actual infected, because our model was able to fit the data quite well. Despite that we introduced intervention into the SEIRD model, we're still able to get reasonable results. This tells us that the Bayesian analysis framework really did a great job, and that's one thing I would like to point out. And also for the recovered, it also did a decent job as well, because the data was able to fit the model quite well. The only thing is the death. It's not really doing great job as we expect, but yeah, it's expected because we know we got this data set from there's so many factors that could lead to this, and then I didn't really go into this, but overall I would say that the model is not behaving too bad overall, and the vaccinated was able to fit quite well as well. Remember that the focus of this study is to understand the impact of intervention measures placed by the government. One good thing is that we're able to get a model that fit the data quite well and can also tell us what these interventions are doing. Are they having a positive impact on the transmission rate or a negative impact? And that is the next thing that I want to talk about here in the results. Remember that when I talked about the transmission, I said alpha naught is when there is no intervention, and when the first intervention took place, then the alpha changed to alpha 1. That is, what is the transmission rate after the first intervention? And that goes on and on until the 14th interventions. Sorry, 14th intervention. Right, and so if we look at this, notice that alpha 1 has a median of negative value, and we have it's significant. Alpha 2 is positive, not significant, and that goes on and on. The interesting thing about this result is that yes, we have some that are significant and some that are not significant. So out of curiosity, I looked at the data set to merge the dates that intervention took place by the government with this result. And the good thing, or should I say one interesting result that I got here that I'm really excited about, is that all the strict intervention placed by the government, for example, closure of schools, universities, and closure of recreational center, travel bans, serious travel bans, and all of that, this one produced a negative alphas. So this tells us that all the strict interventions actually produced a negative transmission media, which means that they were able to decrease the transmission rate reasonably well. And the non-strict intervention, they were positive, which means that they kind of increase it a little bit. Overall, though we might be looking at these changes, they look so small, but if I'm able to scale the data set by 10,000, 100,000 K, I mean, per person, then we'll be able to see the impact even clearer. But overall, we can see that the strict interventions were helpful in reducing the transmission rate, and the non-strict intervention placed by the government did not reduce the transmission rate. So I'm not saying that there will always be a pandemic, but say for example there's another pandemic, this would guide the policymakers, the government, for them to focus more on the strict interventions than the non-strict interventions. And when I say the non-strict interventions, these are interventions that still allow people to communicate, to move around, to mix with others. Say for example, allowing few people to go to their place of work. They still went to work, right? It's just that they reduced the number of people. This is an intervention, but interestingly, we could see here that it increases transmission rate. And when they allow a few number of people to be in their bus when they're traveling, yes, it's an intervention, but still people can have access to communicate. and this is what we can see here, that it's actually increased it a little bit. And one more thing that I would like to mention is the reproduction number. Out of curiosity, we also wanted to know what the reproduction is like before the introduction of the pharmaceutical intervention, which is vaccine. We've talked about the intervention placed by the government, the policymaker. What about the pharmaceutical intervention? So that is the last part that I want to talk about. In this reproduction number, we can see that before the introduction of vaccine. So I just want to mention that the vaccine got introduced on the 420 in this picture. Before the 420, we can see that there is a decrease in the transmission rate as much as possible, especially after the 100. But then there is another increase, so we couldn't really tell if we're in the declining state or the endemic state before the introduction of vaccine. But after the introduction of vaccine, obviously we can see a huge decline, and there is no longer an increase in the reproduction number. So this tells us that the pharmaceutical intervention, which is the vaccine, was also helpful and is in fact helpful in reducing the transmission rate. One thing that I didn't add to the slide is the number of deaths that both the intervention and the vaccine was able to prevent. We know that the strict intervention placed by the government cannot be forever, right? And that is why the pharmaceutical intervention, which is the vaccine, is able to help us live our normal life. People still go to the store as normal. People do their normal activities, despite that this pandemic is still ongoing, right? And we are still able to maintain the reproduction number as much as possible. And this is because there is vaccine. So in order for us to cover up for the strict interventions that cannot be sustainable for a longer time, the vaccine is able to help us live our normal life and still be careful as much as we can. And this is one good thing that we're able to discover in this result. We're able to incorporate intervention measure into the model, and we saw that strict interventions were really helpful in reducing the transmission rate, while the non-strict couldn't really reduce the transmission rates. And we discovered that vaccine was really helpful in reducing the reproduction number, that is the number of secondary infection individuals. And the last thing I would like to mention is that I did a cross-validation on another data set, because this focus was on Qatar. I wanted to know if this model is robust, if it's able to, analyze other data sets. So I used Nigeria data set for the COVID data, and I was able to get a result with pseudo R squared of 0.81, which is quite good. This tells us that the model is robust, and we can use it for any other contouring. The ongoing work is introduction of booster and reinfection rate, and this is ongoing, and hopefully I'll be done with this sometimes next month. Thank you all for listening. If you have any question, please feel free to ask me. Thank you.